Okay, we're going to get started. Hey everyone, my name's Tim. I'm here to talk about mobile performance at Facebook. So what I want to accomplish from a very high level is basically like pull back the curtain a bit about how we think about mobile performance at Facebook, what kind of tooling we use, overall high comments about strategy, and given where we are, what we're thinking about for the future. Okay, so when I talk about performance in the context of this talk, I'm talking about product performance. So when someone's using one of the Facebook apps, how fast and responsive does it feel? And I'm talking about the whole entire Facebook family of apps. So Facebook, Messenger, Instagram, WhatsApp, Workplace. But why do we care about performance in the first place? So for a while, we were seeing this actually like fairly concerning trend in the large Facebook app where engagement was declining over time. And through a very large amount of effort, we were able to reverse this trend. And one of the key things we attribute the reversal to was a company-wide push on focusing on performance and specifically improving the performance of the Facebook app. We were extremely successful at that, and now we have this basically as good of a justification as we could ever hope for justifying, for working on performance. We know that it directly ties into a critical business metric for the company. Okay, so that's performance at a high level, but what do I actually mean when I'm talking about performance? What are the metrics that corresponds to? So we think about performance in a lot of different ways. The most two prominent ones of the company are latency and scroll perf. Latency basically just means how long does it take for something to happen on the screen. Scroll perf is like, as I'm going through, how janky is it? So with latency, we have a standardized way of thinking about it across the company called time to recent content, or TTRC. Basically, so say I'm going to load someone's profile page, the time from when I click on their picture to when their profile is loaded and all the content is ready, there's no more loading spinners or anything. That could come from cache, it could come from network. From the user experience, it doesn't really matter. Just what is the time from when I want to do it until there's recent content on the screen. For scroll performance, we measure large frame drops per minute, where large means that there's 4 consecutive frame drops. And the natural question here is, okay, why not 1, 2, or 3 consecutive frame drops? And I only have time to give you a short answer, but from a high level, it's 2 specific reasons. And the first one is around user experience. So having done user experience research, we basically see that around 4 is where people start to change their behavior, when they start feeling the performance is not great. The second one is more of a, and the user experience answer is sort of prone to change over time as what people expect from their apps changes. And the second is a technical reason, and I don't have time to dive into it, but basically the Android graphics rendering pipeline is extremely complicated, and just because you fail to render 1 frame on time doesn't actually mean that there will be any visible jank even to someone with superhuman eyes. And if you're curious about Googling more about that, the keywords are basically Android triple buffered rendering. Okay, so we talked about the kind of data that comes from the client in terms of latency and scroll perf. And now I want to talk about like how we aggregate that data and how we goal against it. And I want to talk about 3 distinct principles here. So the first one is like the way we aggregate it. So imagine that we're talking about startup performance, and a very basic way to think about this would be, okay, give me all of the startup events and average them. I want to know what's the average startup time. The problem with that, or one specific problem with that comes up, is imagine like, let's say hypothetically, 5% of your users are power users, and they start up the app 20 times more than the typical user. If you're just looking at all the events, when you do an average of that, you are highly biasing your top line number to the power user, and at the expense of users who maybe only start up the app once in this window. And maybe you need to focus on those users because they're having a bad experience. So the alternative to this is something called user-based aggregation, where instead of saying, of all the startup events, what's the average, you'd say, for all of these users, what's the average user startup time? That way you're weighing every user equally. So that's how you would aggregate. And I want to talk a little bit about what the goaling would look like here. So a really common way to think about this again would be, okay, look at average startup time. Our average startup time is XYZ, and we want to try to make it 10% better this year, or 20% better, or something like that. Sort of like, here's where we're at, we want to incrementally get better. The way Facebook thinks about this is pretty much a complete flip of that mindset, We do user experience research to figure out what users expect for great performance for a given interaction, and then we goal on what % of users are experiencing this great performance. So percent good is what we call it. Cool, and the last thing that I want to talk about here is, so just briefly about decreasing average or percent good. Essentially, it's like not how can we get better from where we're at, it's like where should we be and how do we maintain that? And the last principle around here is device classification, and essentially what you want to do is avoid ignoring certain classes of users. So let's say hypothetically 70% of your users are on a brand new phone that's super flashy and high powered, and 30% of your users are on 5-year-old phones that are very low end. If you're just looking at one roll-up number for startup time, you're going to be neglecting the people on lower end devices. At Facebook, we basically classify users based on a framework called device year class, which is open source, and we've talked about a bunch. Essentially, we classify the phone based on what year would it have been a flagship device. And then our goals are broken up into device classifications. The punchline is basically just don't look at one top-line number. Right, so talking about strategy briefly, there's a metaphor that's commonly used around defense versus offense. Defense for performance is regressions are coming up to your metric and you want to fix them to avoid things getting slower. Offense is when you take deliberate effort to find new opportunities and make things faster. The kind of high-level insight here is basically that the regressions that will show up in your app are proportional to the number of code changes, which is proportional to the number of developers. So as your company grows, you are basically forced to figure out a way to deal with regressions, otherwise your app will continually get slower. Like offense is critical in that your app will never get faster unless you focus on offense, but if you don't have a good defensive plan, you won't be able to hold on to your wins. Okay, so I want to talk about tooling, and I want to talk about it in sort of 2 dimensions. And the first dimension, kind of on the x-axis here, is where you are in the development lifecycle. You're developing a new feature, then you're experimenting with it out to a certain number of users, and then it's rolling out in beta and production. And the other dimension that I want to talk about here is sort of on the y-axis, and it's the problem you're trying to solve related to performance. Are you trying to debug a performance issue, or are you trying to detect that one's happening in the first place? And we'll talk about development. So yeah, regular feature developer trying to develop some change. How do we detect performance issues? And a really crucial thing that we have is static analysis. This is a open source tool called Infer, developed at Facebook. And you maybe heard of static analysis. Android linting is static analysis. There's other popular tools like PMD, find bugs, error prone. Infer is basically a state-of-the-art tool in this space, and it works across a bunch of different languages. And we rely on it extremely heavily for finding crashes and performance issues. Here's an example. Someone publishes a diff, Infer comes and comments on it. Hey, you modified this method, and you're increasing the complexity from order 1 to order n for n, some variable in your code. And the issues it flags can get a lot more complex. I highly encourage you to go poke at it. Again, this is open source. You can plug it into your build right away. Another thing that we are heavily invested in is something we call our mobile device lab. It's essentially like a server farm of physical devices where we've put in an incredible amount of effort to optimize for reducing variability, both at the OS level, specific patches we make, to literally like focusing a bunch on cooling these units so they don't get thermal throttled. And so say you publish a diff and you modify certain functions. We know across all the interactions of the app which functions are run during those interactions. So we say, okay, you're modifying the function foo. Which other interactions use that function? Let's run performance tests for them and then comment back on your diff and say, hey, you made these specific interactions faster or slower. And if you change these in a statistically significant way, we gather performance traces from those runs, and then we shepherd you into another tool called comparison view, which I'll dive into later. And that helps you figure out why things changed. And again, so I'm going to talk about comparison view later because, spoiler alert, it's the tool we use across the spectrum to debug performance issues. Okay, so now we have our feature. We want to test it out to some certain number of users. How do we make sure that it's not regressing performance? So I need to talk briefly about the tool that we are using here to report the data. And we call it Quick Performance Logger. It's a tool developed internally to Facebook. It works cross-platform. Essentially what it does is it's measuring very basically like start and stop counters. So here is some hypothetical marker for a time to recent content. And we have a start time and a stop time, and we have checkpoints along the way for things like network requests or render time. And the goal of the library is basically to be as lightweight as possible so we can measure a large amount of users. And this is essentially the foundation for all of our performance metrics. When we talk about latency or any given interaction, it's all reported via QPL. Okay, so we have a tool called Metrics Monitor, and essentially what it does is for every active experiment and then for every interaction in the app, it checks, is this experiment regressing this given interaction? If so, it files a task on you and says, hey, this experiment that you're testing out on some users regresses this specific metric. So then you know, before I can roll this out, I need to go back and work on performance. Okay, so as we transition into talking about beta and prod, I wanted to first address why we need to have performance tooling in production in the first place. Why can't we detect all of these issues locally? And to briefly touch on that, it's essentially a combinatorics problem. Out in production, we'll have any sort of cross-product of different OSs, different device hardware, different network conditions, different experiments that are running, and essentially it creates more conditions than we could possibly test in the lab. And that's not to say that we don't focus very heavily on local detection. We invest extremely heavily in it because obviously the earlier you catch issues, the earlier that are resolved, fewer users are impacted, et cetera. But we're fundamentally not able to catch everything before it reaches production. Okay, so let's talk about beta and prod detection. So when an interaction gets set up in Facebook Infra, someone says, hey, I want to measure performance from my surfaces, they get plugged in automatically to all of these tools. So we automatically generate a dashboard here. The x-axis here is time. The y-axis is percent good, like I talked about, from 0 to 100. Each color represents a different app version. And we can see in the most recent app version, we went from 90% good to 82% good. Of course, dashboards aren't the right way to detect issues in the first place. So we automatically set up alerts for all of these interactions when they onboard with us. So you get an alert for beta production, hey, your metric is regressing version over version. So as we transition into talking about how do we debug these performance issues that we've detected across the board, we're heavily reliant on a library called Profilo, which is developed internally at Facebook and is open source. You can check it out. And essentially what it does is it gathers performance traces from the device. And the goal of the project is to be able to gather as rich performance information as we can without impacting the user experience from production. So through a lot of creative engineering and a lot of effort spent making this highly efficient, we're able to get a tremendous amount of data, including stack traces, resource counters over time. We have manual instrumentation that we've added for various instrumented blocks. We have things like network requests and so on. And it's really powerful to be able to look at individual trace from production for someone's interaction and know what was going on at the system level and the app level. But what's even more powerful is being able to say, across thousands of these traces on test and control groups, what's happening? What are the trends? And we're able to do that across the board. So from traces from the lab with and without your diff, we're able to do that from traces from your experiment for your test and control groups. We're able to do that from production, from version over version. And we do all that analysis with a tool called Comparison View. And I'll talk about all this graph stuff on the right in a second. But on the left, I'm going to talk about the setup. So, hey, we're looking at a regression from a version over version. And further below is all the different kinds of data that you can look at. We have the QPL events that have happened. We have all kinds of ways to visualize the code that was running in Java or JavaScript. We have instrumented blocks that people have added. We can look at class loads, all kinds of things. Now, we're going to look at code just simply because that's very often the most relevant thing. And we're going to look at something called the call graph here. And this looks really complicated, but I'll break it down. It's not as complicated as you think. Each node here represents a function, and we draw an arrow from one node to the other node if that function calls the other function. The blue chunks here are where the code got faster in the test group, and the red is where the code got slower in the test group. So yeah, we can see just looking at this graph, like there's a chunk over here that seemed to got faster or is neutral, and there's a chunk over here that seems slower. Let's go ahead and just like dive into the most red part of this graph. Okay, so we can see all these functions forming this graph on the left, and then on the right we can see a lot of interesting things, like here's the confidence interval we have for this specific one we have selected. Like we're fairly confident that it got slower in the test group. And you can see this entire call chain here with along the left side, like how much slower this function got in the test group. One really useful thing we have integrated here is, so on the left side, these green dots mean whether or not there was code changes to the method or the file. And on the right here, we can see that for this function that we have selected, there was a diff in this version that changed that method. So this gives us enough information to basically be able to say, hey, we're pretty confident that this is relevant to the regression. Let's go ahead and try to revert it and test in the lab to see if this seems like the root cause for the overall regression. Right, so that's a very, very quick overview into detection and debugging performance issues across development through production. One thing that I really appreciate is that the comparison view tool is what we use across the board, regardless of the source of the data, to help debug the issues. And this is an extremely fast overview. Basically, I am oversimplifying and omitting a lot of things in order to fit into this time slot. So if you'd like to talk about this more, feel free. So another thing I want to talk about is where we're thinking about going with this in the future. We've built a lot of really powerful tools for debugging these issues. What we'd like to do is continue to be able to scale this across the company, not just to people who have experienced performance issues, but people who are product developers who haven't even looked at performance issues before. So what we're trying to do is make the process of debugging these issues as simple as possible. So at the top here is like a graph you've already seen. At the bottom is a mock-up of a tool that I'm working on called Performance Insights, where essentially you'd come in via task, like, hey, I know this regressed, and then you'd basically be able to say, the tool would tell you, hey, we saw this regression. We think what's happening here is that users have shifted from hitting the cache case of your interaction to hitting the network. And we think like 10% of users have shifted over, and we think that explains the top line regression here. So how can we basically like guide you through the process so that someone with no performance experience can resolve the issue themselves? And that will allow us to scale out performance across everyone at the company. All right, so that's all that I have for you today. Here is my email if you'd like to follow up. I'm also happy to talk in person. Here's some follow-up resources if you'd like to look at this and learn more. Thank you.